Hello, my name is Samuel Anstis. I'm a Senior GIS Analyst at Jacobs, and I'll be diving into some of the ways we're using FME to help the Environment Agency better understand forever chemicals. So first I'll run you through a bit of an introduction to the project and some of the background on what PFAS are. I'll then be giving you a bit of an overview of our methodology before going over a few highlights and finishing with what we have planned for FME going forwards. Since 2020, Jacobs have been working with the Environment Agency to identify PFAS-related risks to the water environment in England. Using a combination of GIS technologies, we've been working to empower the agency to present and analyse the results of their National Water Sampling Programme in the context of PFAS, looking at potential source sites and environmental risk. PFAS, which you may have heard referred to as forever chemicals, have been identified as emerging contaminants, and as such, the subject area is a fast-moving and ever-evolving one. With increasing scientific understanding and available data, we've been working at developing an approach of risk prioritization scoring, which can be applied consistently on a national scale. The challenge lies with using existing datasets available for the whole country while developing an approach that is flexible as new information becomes available. From the production of national heat maps to the creation of on-demand source site scoring tools, FME is helping the Environment Agency to improve the knowledge and understanding of PFAS sources as they seek to manage the impacts of this area of emerging concern. So, what are PFAS and why are they a problem? Polyfluoroalkyl and perfluoroalkyl substances, more broadly known as PFAS, are a group of more than 9,000 synthetic fluorinated organic chemicals. PFAS can be found in a wide range of consumer products and industrial applications because of their unique chemical and physical properties. This includes all water and stain repellents, temperature and chemical resistance, and surfactant properties. These properties mean they are also persistent in the environment, and some PFAS are bioaccumulative, toxic, and can be highly mobile. While it's acknowledged that there is limited evidence on the human health hazard for many PFAS, with toxicology data for only a limited number of well-regulated PFAS, the Health and Safety Executive and Environment Agency Joint Regulatory Management Options Analysis identified the primary concern with PFAS is to the environment, driven by their extreme persistence as well as mobility and potential for bioaccumulation. Environment Agency reports and monitoring have shown clearly the significant and widespread environmental contamination by PFOS and other PFAS in the UK water environment. But despite declining use and increasing regulation of PFAS in general, there is a significant variability in temporal trends, indicated by different studies, which may reflect geographic variations as well as different pathways. All of this has led the Environment Agency to conclude further research and investigative work was in order to evaluate the sources, including those that are current as well as legacy, that contribute to the widespread nature of these environmental contaminants. To be able to plan appropriately and ensure effective actions are implemented, a better understanding of the environmental risk is required for effective mitigation to be employed. This includes a better understanding of the current and historical sources of PFAS and their pathways into the water environment, as well as the relative significance of these substances in impacting surface water and groundwater environments. So, methodology. We are exploring the relationship between observed monitoring results and identified sources to aid in understanding the potential significance of these sources and help in identification of data gaps where more monitoring data is required. This may also lead to a better understanding of any temporal trends that may exist. A risk prioritization methodology has been designed, requiring the assignment of a risk rating to potential source sites and a multi-criteria decision analysis to rank these source sites. There are three aspects used in the development of the scoring system: site type, environmental setting, and water quality. Scores have been developed for each of these aspects on a generic basis and using national datasets. Site type scores reflect the anticipated PFAS source potential of identified subject sites based on a generic understanding of the potential site activities. Site type scores are solely based on source potential and are not geographically dependent. It is important to note that site type scores are worst case potential generic scores, and the assignment of a score to any individual site does not necessarily mean that PFAS was used on that site. For any site types where sufficient information is available, the scores have been refined for different types of site within that group based on attribute information which is readily available for the whole group of sites. For example, sufficient attribute information is included within the historic landfill site dataset to enable lower scores to be assigned to sites which have only received inert waste. A precautionary approach has been used such that where attribute information is missing, a worst case has been assumed. Some potential source sites include fire stations, air transport sites, landfills, military facilities, major facilities, wastewater treatment sites, and nuclear permitted sites. Multi-criteria decision analysis was used to rank these source sites using a combination of data including environmental setting, water quality, and site type specific information. So environmental setting is the consideration of surface water and groundwater receptors to the risk of PFAS. The surface water heat map detailed information for the risk of rivers and lakes, water abstraction sites, as well as surface water vulnerable to pollution. The groundwater heat map details the risk to groundwater areas designated as vulnerable, areas of soluble rock and karst, source protection zones, and principal bedrock aquifers. The surface water groundwater water quality heat maps utilize water quality monitoring data to assign risk. Outside of FME, water quality monitoring data is scored based on a number of factors such as total PFAS concentration, data confidence, number of samples, and more. An overall site score has been developed for each source site that has been identified using the site type score, the environmental setting scores for that location, and water quality scores for that location. These can be sorted to identify higher priority sites within an area or by site type. As I've mentioned, identification of a specific site in the risk prioritization tool only indicates the potential for that site to be a source of PFAS loss to the environment. Specific assessment is required on a site-by-site basis to assess whether that site has been or is an actual user of PFAS, whether there are plausible pollutant linkages, and whether there is any recorded PFAS impact on the environment in that area. So why did we choose FME? So there were various reasons, but FME's ability to create workflows that allow for a consistent processing approach with benefits including the tool's ability to read and write a vast number of dataset types, the ability to undertake complex data manipulation and conversions, efficiencies found in taking advantage of 64-bit processing, and the fact that FME is a standalone software package receiving constant updates and developments were all considerations in choosing to use it. In using FME, it allows us to future-proof the tools developed to undertake this analysis. To generate the environmental setting heat maps, the processing required was generally quite simple. For the most part, buffers were applied, where needed, to each polygon and then attributed a score based on its inherent features or attributes. An example would be applying a hierarchical score depending on the stated vulnerability of an aquifer. Once the various component polygons had been scored accordingly, we applied a multiplier to each layer, and this allowed us to vary the weighting of each layer and adjust its contribution to the overall score. Following scoring, each feature class is converted to a raster data type and combined to form a heat map. The processing of the water quality heat maps required more advanced analysis. So network analysis of the OS water network data is used to produce multiple smart buffers at specified offsets. These buffers are measured upstream of freshwater water quality locations, and weighted scores are applied to buffers, with scores reducing as distance from the measured location increases. Where a freshwater quality location is located off the network, or for water bodies such as lakes, simple buffers were created from the point of, or body of water where a point fell within. Water quality locations based on saline environments, such as estuaries, were also considered. Following scoring, the vector data is converted to raster data type and combined to form a heat map. Groundwater quality processing follows a simpler approach, buffering locations at intervals, and scores are calculated relating on distance of each buffer from the original water quality location point. Again, following scoring, the vector data was converted to a raster data type and combined to form water quality groundwater heat map. So source sites are processed by extracting scores from the environmental risk and water quality heat maps for both surface water and groundwater. The maximum score within the source site boundary is extracted and applied to the source site. Where this is not possible, a source site is buffered by 25 metres, and this new boundary is used to extract scores from the heat maps. These scores are then joined to the original source site feature class. This will read all feature classes stored within the provided geodatabase dynamically and dynamically write them to a new geodatabase copying the original geometry and schema, but with the added fields detailing the heat map scores. Source site scores are then calculated based on each dataset's inherent attributes, such as the site's size or function. An additional workflow within this tool compares the current permitted landfall data with historic landfall data, and any permitted landfall sites that are found to be present within the historic landfall and landfall data are deemed to be erroneous and removed from the permitted landfall output. Following calculation of the site score for each source site, a combined surface water and groundwater heat map score is calculated prior to the calculation of each site's final score. All scored source sites, as well as all input key intermediary datasets, such as the heat maps, have been made available to the client via a custom app called the PFAS Risk Explorer, developed in ArcGIS Experience Builder. This app allows users to view all their data within a single place. Users can interrogate the data further with integrated screening tools that can create PDF reports based on the user's selected area of interest. So I'll now take you over a few of the highlights in terms of geoprocessing that we performed in some of the FME tools. In porting the methodology for this workflow to FME, we decided to use a blended approach to maintain consistency of output. So previously, before I came into the project, ArcGIS Model Builder was used with a similar aim to achieve an automated approach of updating these core datasets. However, it was slow and it had a habit of crashing when placed under the burden of processing such large datasets. So coming onto this project, the decision was pretty much already made to port these tools over to FME. As I mentioned, we wanted to maintain consistency of outputs, and while FME has some network analysis tools, between wanting a consistent output and the flexibility of Esri's network analysis Python library, we decided on an integrated approach which we thought would be best. The output of which you can see on the slide, showing two buffers tracing the water network from a single origin point. To achieve this, we used Python callers utilizing ArcPy and the NEX network analysis module. So using Python callers, it allowed us to perform this processing in an integrated manner with the rest of our analysis, with the outputs of this processing which could be read back into the workbench mid-process and further analyzed, as I'll show you a little bit now. We did this by getting FME to create a temporary environment to store the output of the network analysis. Paths for the required variables are stored as attributes, which are then fed into the Python caller. The Python caller performs the analysis, which with the required settings to control the distance of the buffers and their width from the network. Once the network analysis was complete, we could read the outputs back into the workbench. Some attributes are lost during the analysis, but these are rejoined before filtering the various buffers and exposing any new fields for further processing. Next, one method we had for gaining some efficiencies within our workflow, due to the national datasets these tools were required to ingest, which varied in detail, it proved quite a task at times, and this was evident in the time it took to run some of these tools. So instead of processing all of our data in one single go, we tried segmenting the input data utilizing workspace runners, which significantly reduced run times from several days to a couple of hours. The workbench on screen was our parent workbench. It's quite simple and passes Ordnance Survey grid IDs in turn to the child workbench. Within the child workbench per run, we extract the OS grid ID from the user parameter and create a bounding box. This is then applied as a spatial filter, limiting the data that's read by the reader. As most of our data was in vector format, while this method would pull in any data that intersected the boundary, processing that extra data was faster than performing any kind of clip. To ensure we did not end up double counting our boundaries, we extracted the bounds of each OS grid. A custom transformer built into the tool, which converts each input dataset to a raster after it's scored, reads in the extracted OS grid bounds, which are then applied to each new raster. This has a twofold benefit. A, it removed any double counting, and B, we ensure that the various component rasters that are combined to make each heat map can be evaluated together as is required by the raster cell calculator. So, where next for this project in FME? We've already begun experimenting with the use of FME Flow for on-demand tools. As an example, one on-demand tool we've created is a screening tool that takes a user-supplied polygon in shapefile format, or it can take a zip of multiple shapefiles. It scores these input shapefiles against our datasets to allow for risk prioritization and provides the output as a download in the user's browser. We plan in the next phase to migrate all of our workbenches to FME Flow, which will allow for even more efficient processing and on-demand updates when new data is made available. Thank you for listening. If you have any questions, I'm happy to answer them.